any chance?
It's true. In fact, not only can you use GPUs to do machine learning, you can use them to do graphics. It's really shocking. So these shading languages are very nice for that.
Well, although you can use it to do graphics, we'll actually mainly be talking about compute programs. So,
dang it.
A bit of a bait and switch there. But yes, I'll be talking to you about the uniformity analysis in the WebGPU shading language. And this was joint work with John Wickerson and Alastair Donaldson at Imperial College. So synchronizing GPU programs is a tricky business. So consider the following CUDA program, which is being executed by 2 threads. I'm also going to use the platform agnostic term workgroup. And in this program, when these 2 threads execute, each of them will have a unique ID. And in CUDA, that unique ID is held in the special variable thread ID x.x. And what these unique IDs do is they let different threads take distinct paths through the program. So when thread 0 executes this program, it's going to try and assign the value 0 to both elements of this array A. And when thread 1 executes the program, it's going to try and assign the value 1 to both elements of the array. And I'm sure many of you will notice that there's a big problem with this program, which is that it has a data race. So the updates performed by thread 0 and thread 1 are going to race with one another. And this is a problem because data races are a form of undefined behavior in many GPU programming languages. So this program may reasonably do anything. To resolve this particular problem, GPU programming languages provide a construct called the barrier. And the way a barrier works intuitively is that when a thread reaches a barrier, it will wait until all other threads in a work group reach the barrier, and then they will traverse it together with a consistent view of shared memory. And so in CUDA, a barrier is provided by this sync threads function. And what that's going to mean for this program is that these first 2 array updates A are going to be performed first. They will reach the barrier, they will wait for the other thread, and then they will move on to performing these array updates afterwards. And we can see that this resolves the data race that we had previously. So barriers are often necessary to avoid data races in GPU programs. But the problem is that misusing barriers can result in another form of GPU undefined behavior. And that undefined behavior is called barrier divergence. So in this CUDA program again, we can see that this time thread 0 is going to reach this first barrier, and thread 1 is going to reach this second barrier. And so I mentioned before the intuitive way that barriers work is that when a thread reaches a barrier, it will wait until all of the threads in the workgroup reach the barrier, and they will traverse over the barrier together. But in this program, there isn't a barrier that is reached by all threads. And so it's not really clear how to give semantics to a barrier in this context. And so for that reason, GPU programming languages eschew barrier divergence as a form of undefined behavior as well. And so this program may crash, it may hang, or it may do anything else. And in practice, it will probably hang. So while this is acceptable for languages like CUDA, where you write your own kernels and it's intended for experts, it is not acceptable for a web-based programming language. WebGPU is a new programming model for the web, and it brings general-purpose GPU computation to the web for the first time. It's centered around a JavaScript API for interacting with GPUs via the browser, and programs are written in a new programming language called the WebGPU shading language. And so this language is designed in a way such that it does not have the undefined behaviors that you would find in other GPU programming languages. So just to give you a bit of intuition about the way Wigzel works, and Wigzel being WebGPU shading language, you might load a web page and it might have a Wigzel program embedded in it. And the goal is to compile that to something that can run on your GPU. And although I've picked something that looks like a discrete GPU here, because it's a web-based programming language, it needs to work on mobile devices, integrated GPUs, everything. And so rather than trying to compile Wigzel directly to GPU machine code, instead, Wigzel is compiled to existing GPU shading languages. And the shading language chosen depends on your system. So on Linux, Wigzel is compiled to SPIR-V, on Windows it's compiled to HLSL, and on Apple it's compiled to MSL. And your browser is responsible for doing this compilation. So Chrome has a Wigzel compiler, Firefox has a Wigzel compiler, and so does Safari. And then this means that the language tooling for HLSL, SPIR-V, and MSL can deal with compiling to something that can run on your GPU. Okay, so the problem is that SPIR-V, HLSL, and MSL all treat barrier divergence as a form of undefined behavior, much in the way that CUDA does. And so if we were to write a Wigzel program that had barrier divergence, so this is exactly the example we saw earlier, where workgroup barrier is now our synchronization barrier, and LID holds the unique variable of each thread. If we compiled this faithfully, we might expect that our browser would hang, our display would freeze, and that would not be good. But thankfully, if we try and compile this program using the Chromium implementation of a Wigzel compiler, we'll get an error that looks like the following. And here the compiler has done a good job. It's rejected this program, and you can see that we've got this error saying workgroup barrier must only be called from uniform control flow. And the reason that we get this error is that the WGSL language specification defines a static uniformity analysis that implementations of the language are required to implement. And the goal of this analysis is to rule out all programs that would have barrier divergence and reject them at compile time. While this is a great idea, this analysis has several problems. The first is that although the analysis claims to be sound, there is no definition of what it means for a WGSL program to have barrier divergence. And actually, it's kind of worse than that, because in the language specification, the analysis is claimed to be sound, but then later in the language specification, it says that a program is defined to have barrier divergence if it is rejected by the uniformity analysis. And so this has a certain circular shape to it. And then the second problem is that the specification of the analysis is just long and imprecise. And in particular, it takes up 27 pages in the language specification, which can make it a little bit hard to figure out what the analysis is trying to do. And in particular, it was often easier to refer to the Chromium implementation of the analysis to try and figure out what was intended. On top of this, implementations of the analysis are just fundamentally hard to test. It's difficult to come up with a way to construct an input program and whether the analysis should accept or reject that program. And then on top of that, when we did do this, we did test implementations of the analysis, we found several soundness and precision issues related to the way the analysis was formulated. So for the rest of the talk, I will talk a little bit about how we approach these problems. So this is the example that I referred to earlier, and barrier divergence relates intimately to this idea of uniform and non-uniform control flow. Non-uniform and uniform are a little bit overloaded here, so I'll tell you what I mean by these terms. By uniform control flow, I mean some piece of control flow that is executed by all threads in a work group. So at the beginning of this main function, both threads would start executing here, so control flow is uniform. In the case of expressions, an expression is considered non-uniform if it would dynamically have different values in different threads. So this Boolean condition is going to evaluate to true in thread 0 and false in thread 1, so it's non-uniform. And because this expression is non-uniform, control flow inside the if statement is also non-uniform. There is no branch in this if statement that will be executed by all threads. And so there are roughly two conditions for dynamically defining barrier divergence. The first is that there is an execution where at least two threads reach different barriers, and we've already seen a case of this. And the second is that two threads reach the same barrier but under non-uniform control flow. And I don't have much time here to give you a precise definition of non-uniform control flow. So hand-waving a little bit, and the precise definition being in the paper. This program on the right is an example where thread 0 and thread 1 will reach the same barrier, but they will take different calls to f, and they will reach that same barrier. And for a bit of intuition, the reason that it's desirable to consider this undefined behavior is that the compiler will probably want to inline that function f, and if it does so, we'll end up with exactly the program we saw before, which has undefined behavior. And like I said before, this is defined completely precisely via an operational semantics in the paper. But without going into any detail, the main rule is this barrier error rule. And in particular, this condition is quite important. And this condition says that barrier divergence occurs if there are two threads that reach different barriers, or there are two threads that reach the same barrier having taken different control flow, with the latter condition being represented by kappa I is not equal to kappa j. And in this case, we transition to a special error case representing the fact that barrier divergence has occurred. Okay, so now we have a rigorous definition of barrier divergence, but we still haven't solved the fact the analysis is lengthy and imprecise. So uniformity analysis is this static taint analysis that is syntax directed and that claims to be sound. And importantly, although it claims to be sound, it's not complete because the analysis is value insensitive. So although the expression LID is equal to LID will dynamically always evaluate to true, the analysis conservatively considers it to be possibly non-uniform. So this is the example we've seen before, a nice contrived example, but it will help to demonstrate the analysis. And the analysis builds a graph, and it is centered around these two special nodes. The first special node is maybe non-uniform, and what this node does is it taints expressions and control flow as being non-uniform. This is a static taint analysis after all. The second important node is required to be uniform, and this is going to indicate that some piece of control flow or some expression must have a uniform value or must uniformly be executed by all threads. There's also this third special node, CF start, and this represents whether control flow is uniform at the beginning of a function. So to analyze this program, we first need to determine whether the expression LID is equal to 0 is uniform. And whether it is going to depend on whether LID is uniform, and we know that it's not, because LID is going to have a different value in all threads. And also, whether control flow is uniform in the branches of this if statement are going to depend on whether control flow is uniform before the if statement. And so we add this second edge from LID is equal to 0 to CF start. Then we go on to analyze the barriers in the body of this if statement. And because a barrier must be called in uniform control flow, to indicate that, we add an edge from required to be uniform to LID is equal to 0, to say that whether control flow is uniform at this point depends on whether LID is equal to 0 evaluates to the same value in all threads. And so now you can see that we have this path from required to be uniform to maybe non-uniform. And this is bad. This will cause the shader to be rejected by the analysis, because some piece of control flow that must be executed by all threads may not be. And so for a slightly more complicated example, which I don't expect you to look at in too much detail, this analysis does work perfectly well with loops. So the program on the left has barrier divergence. And a couple of things to point out. You can see now that this graph on the right has a cycle to represent the fact that we have a loop. And we still have a path from required to be uniform to maybe non-uniform, but it now makes use of this loop back edge to represent the fact that whether control flow is uniform at a loop head depends on whether control flow is uniform at the end of a loop body. And again, we give a completely precise definition of this analysis in the paper, but we won't go through that here in too much detail. Okay, so we also give a proof sketch of soundness based on these two things in the paper, but we won't go through that here. The next problem that we tackled was testing implementations of the analysis. And to do this, we made use of a tool called Alloy. And Alloy is a modeling language that lets you write logical constraints that implicitly describe some system. So, for example, you might write some constraints that implicitly describe the shape of valid Wigzel ASTs. You might then also write some logical constraints that describe how a graph that is built by the analysis is related to a program AST. And this by itself is not very useful, but Alloy comes equipped with a tool called the Alloy Analyzer. And what that lets you do is generate witnesses for these sets of constraints. So what you could do is you could ask Alloy to give you back a witness, and it might give you back the AST that we saw before. It might give you back the program if LID is equal to 0, then barrier, else barrier, and it might give you back the uniformity graph shown on the right. And so while this is not very interesting in its own right, what we can do is add more constraints that give us more interesting programs. So we might ask for a program with 2 loops, for example, and Alloy might give us back this nested loop example, where we have a loop, and a break in the inner loop. And it would give us back the graph that corresponds to this example. Where this gets really powerful is that we can ask for constraints on the actual analysis graph. So we could ask for Alloy to give us an analysis graph that has a path from required to be uniform to maybe non-uniform. And if you recall, that means a shader that will be rejected by the analysis. And so Alloy might give us back exactly the program we saw before. What we could then do is give this program to an implementation of the analysis and check that it does what we think is the right thing. So in this case, it should reject the program because it has barrier divergence. Right, so now we have a way to test implementations of the analysis as well. During this process of both formalizing the analysis in Alloy and testing implementations with the Alloy formalization, we found a soundness bug. And I'll give a brief explanation of this soundness bug. So looking at this program on the left, you can see that we have a loop. And you can think of that like a while true. It's specific to Wigzel, but it's effectively while true. And at the end of this loop, we have a break if expression, which is going to cause the loop to break if LID is equal to 0 is true. And so what's going to happen is, on the first loop iteration, every thread is going to hit the barrier, and then thread 0 is going to break this loop, and all the other threads are going to come back up and execute this barrier. So because not all threads are going to reach the header of the loop on the second iteration, control flow is non-uniform, and so this is a case of barrier divergence. In this case, we would expect the analysis to give us a path from required to be uniform to maybe non-uniform, but this graph shown on the right is the graph that the analysis would have given us. And you can see that there's no path from required to be uniform to maybe non-uniform, indicating that the shader would be rejected. So really, there's a missing edge in this graph, which is the one shown in red here, which says that whether all threads reach the end of the loop body depends on whether the expression LID is equal to 0 evaluates to the same value in all threads. So now we do have the path that we'd expect. So we reported this, and it was accepted into the language specification. Alongside this soundness bug, we also found several precision issues that allow through more shaders, and this is particularly important because shaders that fail the analysis will just not be compiled, so they won't run at all. And again, we also found several just editorial improvements that make the spec more precise and easier to read. And interestingly, we also found a very basic parser bug in Chrome, which was also fixed. Okay, so now we've fixed all those problems. And just to recap, in part of this work, we gave a precise operational definition of barrier divergence for a subset of Wigzel. We gave a precise definition of uniformity analysis. We had several fixes that were accepted into the language specification related to precision and soundness. And we give a concrete alloy model for testing implementations of the analysis. So I guess the main takeaway from the talk is that applying lightweight formal methods to industrial programming languages can reap quite a lot of benefits. And so if you're interested in that, feel free to come talk to me after, and I'll take any questions that you have now.
Do we have any questions in the audience? Two here.
Thanks. Thanks, James. So one thing I was wondering is, so you looked at Wigzel here, but as we've seen throughout the session today, there's a billion GPU languages, and I would like all of them to detect if my barriers are right or wrong. Like, in your analysis, how specific is this analysis to Wigzel, and do you think it could extend to other GPU languages? Like, what assumptions are you making about that?
I think it could certainly be extended to other GPU languages. It's in no way particularly specific to Wigzel. Wigzel has a smaller set of constructs, I guess, than other GPU languages. So the main synchronization primitive for compute shaders is the workgroup barrier. And so I guess you would have to work out how to extend it to other GPU synchronization primitives, but I see no reason you couldn't do so. So another thing that you could do if you did extend it to other GPU programming languages, I mentioned here that the analysis isn't complete. It's not value sensitive. And that's intentional here. The analysis is meant to work somewhat like a type system, so it's predictable. If the analysis depended on the values in the program, you might update your value analysis, make it more precise, and it might be hard to predict whether your shader is going to be accepted or not. And that would just also be hard to formalize in the language specification. But if you wanted to write an extension of this analysis, say for CUDA or another language, you could make it value sensitive, and you could make the analysis far more precise. So that seems like it could be a valuable pursuit.
One more question here.
Actually, two more. No, myself too. Oh, okay, I see. Then I'll just quick. This could be a very dumb question. I don't know much about this barrier thing, but does it normally happen to people trying to put barrier inside the loop?
It depends. There are situations where you'd want to do it. So one of them is, say, you had an array and you wanted to sum all the elements of the array. One way that you can do that is a sort of tree-style reduction where you get threads to add up pairs of elements in the array. So first, say your array is double the length of the number of threads you have. You have each thread take two elements and sum them, take two elements and sum them. You then disable half the threads. You do the same again, and you keep going. In that case, what you need to do is you need to make sure that you synchronize all the threads on each array iteration, or each loop iteration. Otherwise, you're going to have threads accessing overlapping array indexes on each loop iteration, which would be a data race again.
Okay, thank you. I think that about closes it for the GPU session. But don't worry, there's plenty more GPUs to be found here.